Hi, I'm Tom from Sonardyne and I'm here with Eleanor from RS Aqua today and we're talking about ADCP.
So first, do you want to just talk a little bit about Sonardyne, let people know what it is you do?
Yeah, so thanks. So Sonardyne is one of the companies that's part of the overarching Cavalier group. So we have our sister companies, Chelsea Technologies, Wavefront, Voyus, and Iva, and now Forces as well to cover the defence space. But we've really branched out into those areas from Sonardyne's origins. So no pun intended. And so originally we were as Sonardyne we provided sort of electronic and acoustic services to the marine industry. And over time, we've built our portfolio and our reputation. And our core themes are navigation, positioning, communications, and monitoring. So a lot of that has been built on our acoustic modem technology originally. So the ability to talk to between different places underwater using sound waves, essentially transferring information between two places. So that information could be as simple as a timing distance between the two acoustic sensors. And over time that's been built up to include things like data transfer, and like I said before, positioning using our USBL systems and communicating and navigating with our inertial sensors as well. And so leading up to this point, that's been our sort of core technologies. And now with the launch of Origin, we've added ADCP, so measuring currents in the oceans, to our repertoire. And ADCP technology is now also available on our hybrid navigation platform, SprintNav. So we started, so the acoustic communications and positioning technologies, they tend to be in lower frequencies that can operate over longer ranges. But now we're using profiling and that's sort of higher frequency space, so shorter ranges, but sort of richer data sets and more information really.
It's all really interesting. So it's quite a range of things you do there.
Yes, yeah, so we try to fit, provide services and technologies that can solve the marine industry's most challenging problems, really. So that's really where Sonardyne's journey has led us to, and with the introduction of the other companies that I mentioned before, we've expanded our technology range within the Cavalier group to include things like optical communications, sort of software packages for the maritime industry, other marine sensing technologies, so things like turbidity sensors through Chelsea Technologies, and sort of vessel exhaust port monitoring and things like that. So our technology stack is diversifying, if you like, to serve the greater needs of the marine industry going into the future in a more sustainable future and environment.
That's great to hear. So can you explain visually for our listeners what we've got in front of us here?
Right, yes. So in front of us we have an Origin 600 ADCP, an acoustic Doppler current profiler. And what is it? It's basically a cylinder that's about 30 centimeters high, and it's about 200 millimeters wide. The cylinder holds an internal battery, it's an internal rechargeable battery, a bit like your mobile phone. And it also houses the electronics that capture the data, process the data, and store the data for later retrieval. So that's what the bulk of the device contains. And then on the top, you've got this sort of mushroom-shaped bit called the end cap that's a little bit wider than the housing for the battery and the electronics. What's on the end cap? The main bit is we've got 5 acoustic transducers. So these appear as roughly 6 or 7 centimeter diameter circles, slightly different color to the rest of the end cap and slightly recessed. And each of those are acoustic transducers, so we use those to transmit sound into the water. And each one has a sort of very well-defined direction of sensitivity. So they all point in slightly different directions. So you've got 4 of them that are slanted at 25 degrees to the vertical, and they're sort of distributed evenly around the full circle of the end cap, if you like. So you've got one facing north, one facing south, one east and one west, and they're all pointed at 25 degrees to the vertical. And in addition to that, you've got a 5th element, which we call 5th beam, and that points directly vertically, and that one's very useful for measuring waves and turbulence. So we've got a 5-beam ADCP, and what else have we got? We've got a small circular puck on the back of the ADCP. It's also on the slanted edge of the end cap, and that's about 2 or 3 centimeters in diameter. and that's the acoustic modem that's built into the device. So that allows you to communicate wirelessly underwater using Soundwaves with a listening device at the surface. So Sonardyne make acoustic listening devices. So the idea is you have one of those at the surface and the Origin 600 on the seabed, and you can use the integrated modem, acoustic modem as they're called, in the Origin 600 to talk wirelessly with the surface. So that's built into the end cap, that puck as we call it, sort of colloquially. So what else have we got? We've got what we call a battery disconnect. So that's a magnetic device that you plug into the end cap, and that kills all power to the device. So if the device is in transit moving from site A to site B, you plug that in to make sure that you're not going to lose any power. Pull it out when you're ready to put the device in the water, and it will power up and start running. We've also got a fast charge port, again on one of the sloped edges of the end cap. And that allows, once the device is back out of the water, it's depleted its internal rechargeable battery, and you then plug it into mains using a kit we supply with the ADCP, and that will fast charge the ADCP, and it normally takes about 4 hours or so to reach 80% charge, so it is quite quick. So that's another external connector. There's temperature and pressure sensors built into the end cap on the side here. And we've also got a status LED, so that will flash sort of orange when it's waiting to do something and it's idle. It'll flash green when it's pinging away and sending sound waves out and measuring stuff. And it will go red, say, when the battery is depleted and needs recharging. So it's just a nice little visual indication. You don't have to connect anything to the ADCP to have a simple idea about what it's doing, which is useful. And then on the front here of the end cap, we've got an 8-pin wet connector. And that we can use that with an external cable to supply power to the ADCP. So for users who have a cable deployment where they've got a constant source of power, you can keep the ADCP running indefinitely through that port. It's also got Ethernet connectivity, so you can connect it to your computer and download files from the device via FTP. You can stream data out of the device if you want live updates. And so on and so forth. You can communicate with the device via an inbuilt web portal. So you bring up a web page and you can tell the ADCP to stop, to start, to ping faster, ping slower, download files, all this sort of stuff. And then finally on the external wet connector, we've got an RS232 port. So we know that lots of users like to use external sensors like a sound velocity sensor, a turbidity sensor, a CTD. All those sorts of sensors often have an RS232 serial port interface, and so you can send that data into the ADCP via this external wet connector. The ADCP will log that data and can also do onboard processing with it. So that's the overall sort of physical shape of the device and what's on it.
That's really interesting. It's great to be able to get all that data live as well. What's the range on the acoustic comms?
Yeah, so the acoustic modem will work out to a range of about 1,000 meters. So the device itself is rated to 150 meters, so you can place it 150 meters on the seabed, but you can talk to it sort of horizontally, 800 or 900 meters away, and you'll get good comms doing that. So you don't have to be right on top of it to actually communicate with it.
That's great to hear. So before we go into a bit more about ocean currents, what's your background? When did you join Sonardyne?
Right, okay, yeah, I joined Sonardyne almost 5 years ago to the day, so that's good. My background isn't in marine technology or science at all, actually. So my undergraduate degree was in physics, my postgraduate PhD was in experimental astrophysics. And this is a slightly different scenario. Yeah. I did a few postdoctoral research positions as an experimental astrophysicist, working on telescopes and analysing data from that. I left academia because I wasn't very good at it, and I joined a technical consultancy where I really learned a lot about software development, so either from a desktop PC type environment all the way down to embedded technologies, which is sort of very useful and hot topic these days. And it's the sort of technology that ends up inside an ADCP and our other sensors. So that path, although I wasn't applying those skills in the marine industry, the path that led me to Sonardyne meant that all those skills could come together, because in addition to the technology skills I learned on the electronics and software side, all the physics that I sort of experienced in astrophysics actually bears a lot of resemblance to the marine environment in the way that measurements are conducted. So in astrophysics, you're often receiving data more than you transmit. So you end up having these large data sets with lots of interesting things going on that are quite hard to pick apart. And you can use different types of sensing to look at different types of phenomena. And that's really no different from the marine industry. So an ADCP measures water currents, so you're listening for sound and how the currents affect that. And then similarly with video imaging, for example, with our underwater video imaging systems that the likes of Voyis provide, you've got these large data sets coming in from a video feed, and you have to pick out features and analyze what's going on and help the customer interpret the data. So, so although I never started out in the marine industry or had any intention of moving into it, really, I kind of ended up here by accident, but all those skills that I learnt in my background were really sort of brought together to deliver devices like this.
Wow, that's really cool. I hadn't realised there was such a connection between astrophysics and working in the marine environment.
Yeah.
It makes sense, I guess.
Yeah.
They're kind of challenging environments as well, so there's another connection there.
Absolutely, yeah, that's right.
So to go into a bit about ocean currents, why is it important to monitor them? What do you think about that?
Yeah, well, one of the reasons why ADCPs are great devices, they are the device of choice for measuring ocean currents, particularly over range. And the reason they're useful is because they can be used to measure lots of different things. So there's lots of different applications for them. So at the largest scales, you've got things like the Gulf of Mexico loop current, which our Origin 65 is involved with. And that's a large-scale oceanographic current. These are eddies that are shed off of sort of northward going currents approaching the Gulf of Mexico, and they have important implications for infrastructure within the Gulf of Mexico. So historically oil and gas type operations, but increasingly they can be used to investigate the effects of climate change. So that's all quite important. So that's measuring currents, almost out to a kilometre's distance from where the ADCP is. So you can measure large scale currents using those sorts of devices. And then moving down to sort of smaller scales where the Origin 600 here is most applicable. Again, you can use it to monitor infrastructure, things in like ports and harbours, so you can use it to monitor where the motion of material in the water might be going, where you might get build-up of material on the seabed that would stop ships coming in and out of harbours, for example. You also find them being applied increasingly in the offshore renewable environment, so monitoring infrastructure and floating offshore wind, enabling us to determine the heights of waves and whether it's safe to transfer crew from sort of a vessel onto a fixed monopile or a piece of infrastructure. You have to be able to you have to know you can do that safely. So an ADCP can measure, like this one can measure the currents and waves as well, like the heights of waves and where they're going. And so you can make sure that operation is safe for all the people involved. They also get involved in measuring currents at tidal energy sites. At a tidal energy site, you have to make sure that the current that's caused by the changing tides is fast enough that, or of the right speed that it can be used in conjunction with a tidal turbine that's on the seabed. So you've got these blades spinning around on the seabed, or sometimes floating as well. The currents have to be large enough going back and forth past those blades to generate enough electricity to make tidal energy a viable and sort of economically viable source of sustainable and renewable energy in the future. These devices are great as well because they can also measure turbulence metrics in the water, and the turbulence affects the loading on the blades of the tidal turbine and how often you'll have to replace them, and that feeds into the economic model as well of making tidal renewable energy sort of economically profitable and sustainable.
Oh, that's all really interesting. It's such a range of projects you can use them for.
Absolutely.
So in those kind of projects, is it this ADCP that's being used, or is it the larger Origin 65?
Right, yeah, so Gulf of Mexico loop currents, or anything on the large scale where long ranges are involved, or deep water, you often tend to find long-range ADCPs being used, so the lower frequency devices, and that's where the Origin 65 is at its best. That device is also quite interesting because it's not fully an ADCP, it's half ADCP, so it does the current profiling bit, but it also has an integrated high-grade pressure sensor, and like this one, it has an integrated acoustic modem, and the combination of the modem and the pressure sensor can be used to measure the average speed of sound through the water column or the time of flight between the seabed and the surface. And that's used in a process called density mapping, which again can be used to model the effects of climate change and how large-scale currents are flowing through the water column. So you've actually got two instruments in one with the Origin 65. We sell a standalone system called PIES, which has the pressure sensor and the acoustic modem. And we've taken that technology and merged it with acoustic Doppler current ADCP technology, and that's what gives us our profiles of currents as well in one instrument. So that's what that one's used for. This one is used on a sort of small, shallower water projects. So like the floating offshore wind I mentioned, and also ports and harbours. Obviously, that they tend not to be, they tend to be shallower water. And also tidal energy, as I also mentioned. This is a good one for that because it can do currents measurements, waves measurements, and turbulence measurements all from one device. And like the Origin 65, it's got an integrated acoustic modem which allows you to communicate through the water column without the need for cables. And it's all fully integrated, so you don't have any sort of setup process to go through. You just plug it in and off you go. It works.
No, that's really interesting. I hadn't realised there were kind of two instruments in one with that Origin 65 ADCP.
Yes. Yep.
So just can we explain a little bit what an ADCP actually is and how it works? So you mentioned an ADCP stands for acoustic Doppler current profiler.
Yes.
But yeah, it'd be good to understand a bit more
about
how it works.
Yeah, so breaking down the acronym, the A is obviously for acoustic because we use sound waves to measure the water velocities, and we'll go into a little more detail about that in a second. Doppler comes from the fact that the sound waves that we put into the water, what happens is they move into the water, they scatter off of particles in the water, and some of that scattered sound comes back to the ADCP where we can measure it. If the particle is moving with water currents, it will imprint a frequency shift onto the sound wave, and that creates the Doppler effect. So we're all familiar with the Doppler effect from an ambulance going towards or away from us. We can hear the pitch changing, and it's exactly the same physical principle that's used with an ADCP. So in the ambulance scenario, the ambulance is emitting sound at a certain frequency, but as it's travelling, we receive that sound in our ears at a different frequency because there's motion between us and the ambulance because the ambulance is moving. And the change in frequency, so the change in pitch that we hear, that depends on whether the ambulance is travelling towards us or away from us. And it's exactly the same principle with an ADCP. So if the particles that are moving with the water are moving away from us, we'll see the sound stretched out to longer wavelengths, which means a lower pitch. And opposite, if it's coming towards us, then we'll hear the sound at a higher pitch in the ADCP. So by measuring that frequency shift, we can tell how far, which direction the water's going in and how fast it's going. And obviously the signal is transmitted from these elements, which are acoustic elements. So we transmit the sound out of each one, and then it comes back from a scattering particle. And by measuring the time at which we receive the signal, we know how far away that scattering particle was. And so we can measure a profile of the current. So we've got the C part of the acronym and then the P part of the acronym. So by measuring the time at which the signal comes back to us, we can tell how far away the water is, and measuring the Doppler shift within each of those measurements, we can tell how far away we're measuring as well. So that's so that brings the whole thing together. We're measuring a profile of currents, and that's what the ADCP does.
That's very cool. So the larger one, Origin 65, that works slightly differently, doesn't it? It has this separate kind of transducers and reflectors.
Yes.
Can you explain a bit more about that?
Yeah. So if I start with the Origin 600, we've got these acoustic elements, and they're what we call monolithic transducers because they're a single piece of material that emits sound into the water when you apply an electrical current to it. So that's the standard way of doing it, and that's the way the Origin 600 does it. That's the way our Syrinx DVL does it. That's the way our Sprint Nav and Sprint Nav Mini hybrid navigators use acoustics, all through this simple idea of having a single element that can transmit sound into the water. So that's all fine. With the Origin 65, we've taken a different route because with an ADCP, each element has a sort of a region of sensitivity where it can actually measure, and that's actually really directional. So instead of measuring the current all around it, and you sort of can't tell which bit's coming from where, the region of sensitivity, which we call the beam, is actually very, very directional. It's only about 2 degrees across on the Origin 600, and that's a fairly standard width of the beam for commercial ADCPs. But the problem is when you have a device where you want to measure currents over a long range, so at low frequency like the Origin 65, you can't achieve the narrow beam width that you want without making the transducer big. So there's like an opposite relationship between the two. So you've got two options. You can either build a really big transducer in order to achieve the narrow beam width at low frequencies. But the problem with that is that as the transducers get big, they obviously get more expensive, there's more material involved, they're more sort of complex to make. And because they're large, they've got a big surface area on them, lots of bonding glue around them. So when you take them in and out of deep water regularly, that bonding can fail, and the transducer has to go back to the manufacturer for rework, which sort of results in downtime and lost money for the user. So we wanted to try and think about a way that we could potentially get around some of those problems. So if you're in shallow water looking downwards, for example, it's not a problem because you're not taking it in and out of high pressure routinely. So that environment's okay. But for deep water operations, like the Gulf of Mexico loop currents I mentioned earlier, you have to be able to have transducers that can withstand that pressure and do it repeatedly without breaking. So what we've done with the Origin 65 is we've got the same simple transducers that we see here, sort of monolithic transducers, but we make them small, and at low frequency that means you've got a wide beam. So that's not so useful. But what we do instead is shine that down onto a parabolic reflector, which is the same shape as your home satellite dish, effectively. It's the same type of system. And in doing that, we bounce the signal off the parabolic steel reflector, and the shape of the reflector focuses that wide beam from the projector into something much more narrow, which is a more conventional ADCP beam width. And that's how we form our narrow beam that you want from an ADC operation without having to resort to a big, expensive and failure-prone transducer. So the small transducer we use, it's only about 4 centimeters across, and that's you can make those depth rated, as we call it. So it's very robust to pressure cycling, and so we have a cost saving there, a robustness saving there, because we're just using a steel plate in conjunction, which doesn't really fail very much, and we still get the same performance. And one of the other nice things about doing it that way is that the reflector, the satellite dish bit, you can make it big or small depending on what sort of beam you want. And so we've actually made it a little bit bigger than you'd expect conventionally to give us a narrower beam. And the good thing about doing that is that you've got more what we call directivity. So you've got more sensitivity in a particular direction compared to conventional ADCP beam widths. And that means that when you deplete the internal battery, you're using the power more efficiently in that one direction rather than spreading it out too much with a narrower beam. So yeah, there's a few different things going on there. It's but overall, it gives us really quite good performance, and we get the robustness benefits as well.
That's a really innovative design. It's nice to hear something like that. That's working really efficiently. Do you think there'll be a increasing requirement for these big deep water ADCPs with climate change affecting these larger ocean currents?
Yeah, it's a good question. I think generally there's going to be a need for more measurements overall. So now that climate change is a bit more in the public domain and more visible, people are sort of more concerned about it. They're going to want to monitor it more and more. And there's a place for ADCPs all across the depth range because climate change affects everything. It's everywhere. And so yeah, I can see an increasing demand for deep water applications where you want to do long-term monitoring because smaller ADCPs like the Origin 600, they're good for sort of relatively short-term monitoring short-term change. But when you're in deep water, it takes a long time for some of the effects of climate change to affect the whole environment, and so you have to be able to track that change over a long period of time. And so to do that, you need a device that can go down on the seabed very deep for a long period of time so that it can sample that change, and so the likes of scientists can start tracking its effects and feeding it into climate change models so we understand the whole phenomena a bit better. Yeah,
it'd be really good to understand that better and see what happens with that research, because we know that it's going to have a massive effect on our climate.
Yep.
So much of our warmer temperatures come up through ocean currents, and
right.
That's why it's not so cold here in the UK.
Absolutely, yeah.
So another effect of ocean currents is coastal erosion and those kind of things. Have any of these ADCPs been used in those kind of projects yet?
Yeah, I mean, we've been involved in coastal projects, mainly more in the offshore renewable tidal space than coastal erosion. But there's nothing to stop this device being used in those kinds of environments. So they're very good for not only monitoring the currents, but also the sort of sediment loading in the water, so you can see where the eroded particles are going and things like that. So I think there's going to be, as you point out, increasing demand for those kinds of applications, and an Origin 600 is a good fit for that.
That's really useful.
Yep.
So going back to ocean currents,
Yeah.
they also cause a lot of plastic aggregation on coasts or in gyres out in the ocean as well. Do you think the
Yep.
ADCPs can be used for kind of working out where that plastic is, why it's aggregating in certain areas, and then working out how we can collect it from those areas?
Yeah, so there's certainly a part to play for ADCPs in helping that kind of operation. So if there's plastics in the water, depending on what their size is, they can appear in the ADCP data. So we often use the current profiling part to determine where currents are flowing and therefore where the material, the plastic, might be going. But you also get, and it comes back to what I was sort of saying before about the rich data that ADCP provides, you also get the sound waves scattering off of plastic particles, and you can measure the intensity of the sound that scatters off the particles. And that means that you can sort of track material in the water via its echo intensity, a bit like an echo sounder. And so by measuring the signal strength received, you can detect where there are density of material in the water, and the currents tell you where they're going. So with a single frequency device, like most ADCPs are, you can tell that there's material there, but it would be hard to differentiate, say, a fish, the effect of a fish from the effect of a lump of plastic floating around. And obviously, as plastic breaks down into microplastics, then you've got different effects going on, and those are sensitive to the frequency of the device. So there's actually really complex environment and complex things going on, but ADCPs can certainly help to determine if there's plastic in the water and where it's going, or material in the water, I should say. Regarding the sort of cleanup operations that you sort of see in the news, then yeah, you've obviously got vessels moving around, towing big bits of kit and bringing sort of harvested plastic, I'll call it, back onto the vessels and things like that. So it's important to know what the currents are doing in those kind of environments, because the vessels may need to hold position, so you need dynamic positioning capability, and obviously that's affected by the current, so you need to measure where the currents are going and whether that direction and speed is changing, because that's going to affect your vessel operations. And again, I imagine that that sort of if there's rough environments, then that affects crews on board the vessels and things like that as well. So ADCPs, as we talked about before, can measure waves and things like that. So so I think there's loads of different aspects that ADCPs can help with, whether they're vessel mounted or seabed mounted, like Origin 600 might be, to help that kind of operation and characterise how much material there is in the water and where it's headed.
I guess on a similar line to that, you can also use that kind of information to understand the life cycles of things like jellies and baby turtles, because they get caught up in these currents as well and drift around.
Yes, yeah.
Do you know of many projects where they've been used for that purpose?
Yeah, I've heard of such projects. I'm not personally involved with them at the moment. Again, I think it comes back a little bit to the fact that with some of these ADCPs, you only have a single frequency, so you may need more than one in close proximity, because again, something like a fish or a turtle will have a different acoustic signature to a piece of plastic, and so you need to be able to measure at multiple frequencies, or you may need to be able to differentiate the two. So yeah, I'm sure there's a part to play of ADCPs in doing that kind of research.
Yeah, even if you can't differentiate the actual organisms themselves, I guess you can see where the current's going, so where they're likely to be taken, especially these ones that don't really swim for themselves, like the jellies.
Absolutely,
some of them
yeah.
just drift around in the currents during their lives. So
yeah,
that's really interesting. So we've talked about the basic capabilities of the ADCP, but you also mentioned there's onboard processing with it. So can you tell me a bit more about that?
Yes, yeah. So obviously our ADCPs do the basics right. So we can measure currents, waves, turbulence, the same way that many existing ADCP users would expect. And we talked about the acoustic modem and the communications you can do with it. So starting and stopping the ADCP to save battery life, reconfiguring it, checking on it when it's on the seabed, all that sort of activity can be done acoustically and wirelessly. So that's quite helpful. So if you're a surveyor and you deploy your ADCP, you can check it's gathering data before you leave the site, so you know you're going to get the data that your contractor needs. The onboard processing is almost like the icing on the cake of all those features. So in addition to doing the basic currents and being able to monitor the ADCP acoustically and wirelessly, our onboard processing facility allows you to process data on the device. Now, on its own, that would be a bit useful, because you can sort of boil the data down into the answer you're after, and you can get a quick look when the ADCP is out of the water. But what it really does is it enables you to, it sort of opens this window up for live monitoring and data harvesting. So the core data formats that we produce, so our proprietary high resolution formats as well as industry standard PD0, they're really a bit too big to get through the limited bandwidth of the acoustic modem. So, so it would be very inefficient use of time, battery, and so on, and the acoustic modem to offload these large data formats that way. But with the edge processing, you can define, the user can write their own algorithm that sits on the device that bakes all that data down into just that little bit of information, the yes/no answer or the green light, red light answer that they need. And once you've got the data that small, then that can be exported over the acoustic modem very efficiently. So to give an example, we've written an edge application. It's a bit like an app that goes on your smartphone, but the difference is here we've written it and it goes on the ADCP. And that produces metrics for waves. So we can tell you what the wave height is, what its peak period is, what the zero crossing frequency is, what the cross-directional spectrum is, and all these sophisticated things. It takes, that's gigabytes and gigabytes of data, because you have to collect a lot of it to be able to process the waves and get good accuracy measurements. You can't get gigabytes of data through the acoustic modem, but our onboard edge processing does the processing that you would normally do offline on your desktop PC in the ADCP itself, and it will bake it down and it can tell you this is the significant wave height, and that can be exported through the acoustic modem more or less in real time. And so if you're monitoring a crew transfer operation, for example, and you want to know what the significant wave height is right now to ensure safe operation, Origin can tell you right now. You don't have to wait to get the ADCP back or use any other means. Another example might be, even if you just want to know what the average current is throughout the water column, you can get that from a PD0, a single PD0 record, but it might take a while to come through the modem. Because it's big, it might not be very reliable, but that's really just 3 numbers, just a couple of bytes. But with onboard processing, you can bake all that data down into those 3 little numbers. Off they go through the modem. They'll tell you what the answer is then and there. So that's just the beginning, though. So we've written 4 apps that we offer as part of our edge processing capability. So you can measure waves is one of them. Turbulence is another one. So turbulent kinetic energy metric, how much turbulence there is in the water. Background currents, and we also do a quality control edge app which uses the CARTOD standard, which is like a standard well-known formalism for calculating the quality of the ADCP data. So if you want to make sure that your ADCP data is good before you leave the site, you can use our CARTOD app. It'll do some processing and it'll tell you, yep, the data is good, you're going to be fine for your deployment, or it might tell you this environment isn't so great, you might want to consider redeploying somewhere else. So those are the apps that we provide, and they come with as part of the edge processing. But people who purchase the edge capability on the device are also supplied with the edge software development kit, or SDK. And that means that if you've got programming resource of your own, so a programmer that works at RS Aqua, let's say, then you could write your own edge application that will specifically meet the needs of one of your clients that may have needs that are different from the edge apps that we provide. So you can customize the way the data processing is done, deploy your app onto the ADCP, and receive your data from the seabed to the surface acoustically, and therefore meet your client's needs. And Sonardyne doesn't need to be involved in that process. Once you've got the ADCP and the Edge SDK, it's like a sandbox. And we've been very careful to sort of constrain that sandbox so you can't break the core ADCP functionality. So you'll still get all your PD0 at the end, but if you choose to use it, you can customize the data in a way that is unique to your client's requirements. And that means you don't need to have back and forth with Sonardyne about adding new features that may not fit into our business model or any kind of future roadmap. You're sort of decoupled from that, and so it's sort of a highly customizable sort of environment that you can use.
That's great. That makes the applications for it literally endless if you can just kind of customize it.
It does, and it comes back again to what we were saying before about external sensors, for example. So we've experimented with an external turbidity sensor. So that sends its data over RS-232 into the device. So ADCP will power the turbidity sensor. It will send its data into the device, that data gets logged anyway, but it also gets passed to the edge environment. So if sediment loading is important for you, you can combine that turbidity sensor measurement with the ADCP measurement in the edge environment and export that fused data acoustically, and so you can get the answer from both sensors in one shot, and you don't need to do anything else.
Wow, that's amazing.
It's pretty cool. Okay, well, I think that wraps it up. Eleanor from RS Aqua, thank you very much for coming in today. It's been a pleasure, and I hope that some of the information has been interesting and useful, and I'm sure we'll cross paths pretty soon.